The term that we're going to talk about now is what we call the electronegativity, and the electronegativity is just because I want to make sure that you're not confused with the electron affinity. Electron affinity is a property of the atom or of the element that is not dependent on being in a bond. So it's like the ionization potential. It's a property of the atom. It depends on the nature of the atom, its ability to acquire electrons or to get rid of electrons. The electron affinity is the ability of the atom to get one more electron. It has nothing to do with the bonds. But for electronegativity, it is a property of the atom while being in a bond, while being in a covalent bond. So it is the measure of the tendency of an atom to attract the pair of electrons in the bond to itself, to get them closer to it than being closer to the other atom that is sharing the electrons with it. We would expect that fluorine is the most electronegative element. It has a smaller molecular size. It has high ability to attract the electrons, while on the other side, the group 1A is the least electronegative. One scientist whose name is Pauling has made this electronegativity values. He put some just generic numbers or a scale that is for somehow he was able to calculate the values and put them on the scale of one from 0 to 4. The fluorine was the maximum, or had the maximum electronegativity, or maximum value of electronegativity, and cesium has the least value of electronegativity. Just to take a look at it, we will see that as you go from right to left, the electronegativity decreases, and this is expected because as you go from here to here, the atom gets more tendent to get rid of the electrons than to acquire the electrons, and that's why it's not gonna be like very or it's not gonna be able to attract the electrons of the bond to it rather than getting rid of it. And this is applicable. We have here 3, 2.5, and this is 0.9, 2.8, 0.8, 2.5, 0.8. So as you go from right to left, the electronegativity decreases. And as you go from top to down, the electronegativity decreases. And this is also expected, because in this case, as you go down, the number of electrons around the nucleus gets more. You have more barriers between the nucleus and the bond, the pair of electrons that form from the bond, and as this distance increases, the attraction force between the bond and the nucleus decreases, so its ability to attract the bond to it is weaker. So this is like an important thing to keep in mind. Let's take a look at the numbers, and just we will think about different alternatives of the bonds that can form. Let's say we have a a bond that forms between an element here, potassium for instance, and an element here, let's say fluorine. So potassium fluoride, we have a very huge difference in the electronegativity, and this huge difference will not only make fluorine attract the electrons to itself, it's gonna make the electron transfer completely from the potassium to the fluorine atom. And this is how the ionic bond forms. So we would expect the ionic bond to form between two elements that have a very big difference in the electronegativity. In other cases, we would see that for instance, for which is the other extreme, if you have two atoms that have the same electronegativity, for instance, for chlorine, you would see that for chlorine molecule, it is formed of two chlorine atoms that have exactly the same value of electronegativity, and in this case, the covalent bond would form, but it's a stable. We would not expect one of them to attract the electrons more than the other because they both have the same values. The third case, which is the interesting case actually, if you have something like water or HCl, you have a molecule that has a value of electronegativity and another that has a higher value of electronegativity. And in this case, I would expect that the bond will be attracted more towards the oxygen than towards hydrogen. This is exactly what we see here for two chlorine atoms. The bond is in the center, but here in the HCl, the chlorine has higher electron affinity, electronegativity, and that's why the electrons will spend more time here than they spend in the hydrogen atom. So it's not gonna be a symmetric bond, and this results in a formation of a partial positive charge here and a partial negative charge here. Electrons are not totally transferred from here to here, but they are partially available here more than they are here. That's why the negative or partial negative charge forms here, and this is a partial positive charge forms here, and this is called, and there's some call or sort of polarization of the charge, and that's why this is called a polar covalent bond, because the bond is polarized towards one of them, or the two atoms than the other. And this equation can be used to calculate what we call the dipole moment, or how much is the bond transferred toward one of the molecules than the other. And this is the reason, and the polar covalent bond, it's important to know this, because it's like one field of study in thermodynamics is the polar compounds, and the way the molecules are, or the bond is formed, and the partial charges has a very strong effect on the behavior of the molecules. And there is one new type of bonds form uh, just because of this. And this bond is called the hydrogen bond. And the hydrogen bond forms because we don't have a molecule just by itself. We have molecules that have other molecules around it. We have partial negative charges around and have partial positive charges. So these charges like to get closer to each other. And this makes the molecules more bounded together and increases the attraction force between them. And this makes the molecules harder to boil or harder to evaporate. And this is what we see here. We see here hydrogen sulfide, hydrogen selenide, and hydrogen beryllium. I'm not sure what its name is. I just gonna take a look at the electronegativity values from the table for these. These are oxygen, sulfur, selenium, tellurium, and you'd see this 2.1, which is exactly like hydrogen. This is a little bit higher, this is a little bit higher, and oxygen is way higher than all of these. Okay. I'm gonna take a look at the periodic table. I don't know, where was it? Yeah, here it is. And in the periodic table, you see the oxygen, sulfur, selenium, tellurium, and you see that the molecular weight of oxygen is 16, sulfur is 32, selenium is 78, tellurium, I'm sorry, is 127.6. So this is how many times? It's like 9 or 8 times heavier than the oxygen atom. But despite having this very big difference, I'm sorry, you'd see that the molecular, or the boiling point of water is way higher than all of them. And I would expect, if I'm extrapolating, that this is how the boiling point decreases at the molecular weight decreasing, that the water would be something here, something around this. But this is not what takes place. Hydrogen, because of the formation of hydrogen bond, is way higher than the molecular, or the boiling point of the other two, and way higher than what is expected from it compared to the other molecules of the same class. So this is actually a blessing from God, because you would expect that if you want to drink some water, and this water is boils at like 170 Kelvin. 170 Kelvin is like negative 100 Celsius. You have to go to negative 100 Celsius to be able to drink water, and this is gonna be totally impossible. So the hydrogen bond is very important for this case. We have two other types of bonds that we will not go into a lot of details of them, just will quickly talk about them. The first is what we call the coordinate bond. The coordinate bond is similar to the covalent bond. We have a bond that is shared between two atoms, but this bond is originally from, or the electrons in this bond are originally from a single atom. They are not from two atoms. For instance, this is a carbon monoxide atom, Carbon has 4 electrons in the outermost energy level. Oxygen has 6. So it shares 2 electrons with carbon. So oxygen has 2, 4, 6, and 8. Each one of these lines is a 2 electrons, so it's 8 electrons. So oxygen now is saturated, it's happy, it is in a good state. For carbon, it has 2, 4, 6, so it needs one more pair of electrons. And for the molecule to be in a stable state, the oxygen shares this, what we call the lone pair of electron. And this lone pair of electron is originally from oxygen, not from carbon and oxygen. And this is how the bond is different. It is different from the origin of the electrons. Where did they come from? The same for ozone. We have here oxygen and oxygen. Just forget about this now. This oxygen has 6 I'm sorry, has 6 electrons, and this has 6 electrons. They share these 2 pairs of electrons, so they are now happy, they are now saturated. And to form the ozone molecule, this oxygen shares, or this oxygen molecule shares the 2 electrons with the new oxygen atom. These 2 electrons are originally from the first atom, not from the other. And this is why we call this the donor atom, and this is the acceptor atom. Okay, and because the coordinate bond is very similar to the covalent bond, sometimes they call it the coordinate covalent bond because it behaves the same way. It's just the difference in the origin of the electrons. The last one, or the last bond that we're going to discuss today, is the metallic bond. And the metallic bond is, again, we discussed before in the previous chapter when we were talking about the melting and boiling points of the elements in the periodic table. We mentioned that the boiling and the melting point of metals is, or the mechanical properties of metals is dependent on the electron cloud. And we mentioned that the electrons in the outermost shell are not only rotating around the atom, they are rotating around the whole atoms. They're rotating around the atoms in the in this metal. So they form like a cement that is bounding all the atoms together and holding them together, and it's responsible for the high electric and mechanical and thermal conductivity of the atoms. They are responsible for the good mechanical properties of the element. And it's different from the ionic bonding, because the ionic bonding, the atoms are stationary, the ions are stationary. There is no motion of the charges, but here the charges are free to move between the atoms as they want. And again, we said that it's responsible for the physical and mechanical properties of the metal, and it was kind of explanation why lithium has higher melting point than sodium, despite having lower molecular weight or atomic weight. So if you're interested in more details, I'm not gonna just repeat what I said before. Please go back to the transition elements video in this series, and you would find the details about that. So finally, I found this is like a very nice photo. It is showing the difference between the bonds. So it says for the covalent bond is to love, is to share. So they are sharing the electrons, one from here and one from there. For the metallic bond, the love is to let the love flow. So it's so they are expressing the electrons by the word love. So the love is flowing between the atoms. And you see here they're all of the same type. It's not like this. For the ionic bond, it is give for love, but never give up on love. It's giving the electron to the other atom. And for coordinate bond, there can never be too much of love. It says 2 instead of 2 anyway. So these 2 electrons are originally from the blue atom, not from the yellow one. So this is all for today. So thank you, and I'll see you in the next video, inshallah. Goodbye.